Okay, one thing you are sure to get on your AP Physics test is plenty of graphs that you need to interpret. You need to be quick and accurate at doing this, so let's just practice this right now. All right, so when you look at a graph, the first thing you need to do is you need to look over at the y-axis and see what that's all about. That tells you most of what you need to know. Ask yourself, what does it mean for it to have a positive or negative value? What does it mean to have a zero value? Then you need to ask yourself, what does the slope of this graph mean? And the best way to do this, look at the units associated with the y value and say, well, if I divide that unit there, say meters per second, by the x value, which is seconds, what do I get? Well, meters per second divided by seconds, that's acceleration. The other thing is actually what the area means. Okay, so if I multiply the units of the y-axis by the units of the x-axis, what does that give me? If I have meters per second on my y-axis times seconds, that leaves me with meters. Oh, it's displacement. So those are the three things. What does the y values mean? What does the slope mean? What does the area mean? And as long as you do that, you're usually going to be quite fine. But let's just go through all these things one at a time. So let's start with displacement graphs, or position versus time graph. So the first thing is the y values tell me where the object is, whether it's in the positive direction from negative direction or the positive direction from me. So I look at the intercept. This is my starting position was -8 meters or 8 meters to the left of me. I ask yourself, what does the x-intercept mean? Well, it's the time, in this case 4 seconds, in which the object was 0 meters away from me, so it was right in front of me. You need to ask yourself what the slope means. Well, the slope in this case would be meters divided by seconds, so the slope is velocity. If I have a constant slope, I have a constant velocity. If I have a positive slope, the object is moving in the positive direction. If I have a negative slope, the object is moving in the negative direction. And to find the slope, you just say change in y over change in x. So in this case, I get 2 meters per second, positive 2 meters per second. So it's got a positive slope. It's moving in the positive direction. Even though it starts off in the negative position, it's always moving in the positive direction. The other thing we can do with a displacement versus time graph is we can look at it, we can make inferences about accelerations, okay? So if I see a straight line, that tells me there's no acceleration. Well, if there's no acceleration, that means the sum of the forces must be 0, so there's no acceleration. If I see a curve, then there is acceleration. And then I want to ask myself, what is it a positive or negative acceleration? So what I say is, well, if I see a smile, it's a positive acceleration. If I see a frown or part of a frown, it's a negative acceleration. Let's think about this. This object started off, is always a good idea. Look at the very first part of the graph. I see a negative slope. That means I have a negative velocity that's fairly steep. So it's moving fairly quickly in the negative direction. Over time, I reach a slope of 0. So that means it's not moving anymore. So it's momentarily stopped. And now I'm getting a progressively steeper positive slope, so it's moving faster and faster in the positive direction. So it slowed down in the negative direction, stopped, and started going in the positive, and started accelerating in the positive direction. Conversely, I have the negative acceleration. Same thing. I start off with a steep positive slope. I end up with a slope of 0. So it was slowing down in the positive direction. It stopped, and then it picked up speed in the negative direction. So velocity versus time graph is probably the one you're going to see the most of on the test. And so it's really important that you dial in and make sure you understand exactly what these are telling you. So again, what is the y value tell me? This is how fast you're moving. Negative means you're moving in the negative direction. Positive values means you're moving in the positive direction. Doesn't tell me where you are. It tells me which way you are moving. So I look here, this value here, the y-intercept, that is my v initial. And that's something you definitely want to know. What is the initial velocity of the object? I see as time goes by, I'm getting closer to 0. That means I'm slowing down. I was moving in the negative direction, but I'm slowing down. I stopped at this point in time because my velocity is now 0. And now I'm picking up speed in the positive direction. So this would be like well, no, it wouldn't work here. Never mind. Okay. Uh, so the slope then, what does the slope mean? Well, the slope would be meters per second divided by seconds. That's meters per second squared. That's acceleration. So in this case here, if I say change in y over change in x, I get 2. But in this case, it's meters per second, which is acceleration. And I can ask myself, what does the area mean? The area would be meters per second times seconds, which would just leave me with meters, which is displacement. So let's just try one here. I've got this one here. I start off at positive 6. 6 seconds later, I'm going 0, so I'm slowing down. And if I do change in y over change s, I get -1 meters per second squared is my acceleration. If I take the area, I would say 6 times 6. So I'd make this rectangle and I'd cut it in half. So 6 times 6 divided by 2 gives me 18. And meters per second times seconds leaves me with meters. So my displacement then would be 18 meters. Acceleration versus time graphs, you do get those usually when you see them. It's a flat line like this. I have two different objects shown here. Sometimes you'll see it goes from here to here, but the acceleration is usually going to be a flat line. It doesn't have to be. You can have variable forces, say with springs or something like that. An oscillating system we'll talk about later, but usually it's a flat line. Okay, so this is telling me that this object A is accelerating in the positive direction at 5 meters per second, and object B is accelerating in the negative direction at 10 meters per second. Now, if I take the area of this, so if I find the, remember the area is always between the line and zero, not to infinity, to zero, okay? So I take this area here, it would be 5 times 8, that would be 40. So that tells me this object has a change of positive 40 meters per second in its whatever its initial velocity was. I have to change it by positive 40. This one, whatever its initial velocity was, the delta V is going to be 10 times 8, negative 80. I can also use this to make inferences about the net force acting on objects. Remember, net force causes acceleration. So let's just say I know I have a 2-kilogram object. Well, I have a 2-kilogram object, and it's accelerating at 5. Therefore, the net force on it at positive 5 is positive 10. Oh, I've got a 2-kilogram object, and it's accelerating at, I think I just heard my first cuckoo of the year. I love hearing cuckoos. Okay, so I can say, well, 2 times negative 10 is negative 20 is the net force. You will see collision versus time graph. Sometimes both objects are shown, sometimes just one. But if they're both shown, here's the way you can tell. You can tell two things from it. You can tell the relative masses of the object, and you can tell the type of collision. So whichever object changes velocity less has a greater mass because it has more inertia. Whichever changes more has less mass, it has less inertia. And I can look at the change in the gap between the two objects' velocities to start with and final. And from that, I can make an inference about the type of collision. Therefore, the change in the mechanical energy as a result of that collision. Our momentum's not going to change, but the kinetic energy can. Let's just take a look at how we do this. So in this one here, I'd say, well, the velocity was the difference between here and here is 4, and the difference here is 4. There was no change in this gap. Therefore, there's no change in mechanical energy. I must have had conservative forces involved in the collision, like say a spring. And so in this case, that is a perfectly elastic collision. And I can look here and say, well, this one changed by 2, whereas this one changed by 6. So the blue one must have 3 times the mass of the red one, or conversely, the red one has a third the mass. If I look at this one here, I can see this gap narrowed a little bit, indicating that there was some loss of kinetic energy. The mechanical energy went down as a result of this collision. I had non-conservative forces, probably the normal force between two colliding objects. Now, and then I can tell here that they both changed by 3, so I can tell that the mass of these two objects was the same. I look at this one here, and I see that, again, like this object here has 3 times the mass of this one here because it changed by 1/3 as much. But I can see they both came together, and they're traveling together afterwards, so that this gap, if you will, went to 0. That tells me that's a perfectly inelastic collision. I have the maximum decrease of kinetic energy I can have while still conserving the momentum. Now, you don't fall for this trick here. So sometimes you'll see a force versus time graph that's showing a collision. And remember, anytime there's a collision, it's Newton's third law. Equal forces act in opposite directions for the same amount of time. So at all points in time, the force is going to be this equal but opposite. So, and they'll try to trick you sometimes by having different masses and different velocities. But remember, in a collision, anyway, anytime there's an interaction between two objects, it is an equal force in opposite directions for the same amount of time. Somehow I have this here twice. Don't ask me why. I'll fix that. Okay. So if I have a force versus time graph, another thing I can do is I can look at that and I can say, well, what happens if I multiply? Remember, so if I say, what does the area mean? Well, in this case, area is force times time. Well, force times time is change in momentum. So in this case, the area would be, remember, it's not from here to the bottom, it's from here to 0. So I would say 2 times 15, that gives me 30. So the momentum changed by 30 kilogram meters per second. So again, like if I looked at something like this, I'd say, well, let's just say I knew I had a 5-kilogram card initially traveling at 1, so I know what the momentum was. It was 5 to start with. I can find its final velocity by saying, well, okay, so let's say the area here is going to be 4 times 10, that's 40, but I only have half of that, that's 20. So the force times time is 20. That's the change in momentum. This is going to equal the mass times Vf minus Vi. And when I solve it, I can tell what the velocity was. If I get a force versus distance graph, the other thing to keep in mind is that, in this case, not versus time, but versus distance, force times distance is work. So the area on this graph tells me how much the mechanical energy of the object changed. So if I have a positive change, that means the object gained kinetic energy and it's going faster. Uh, and so let's just say in this case, so okay, well, all I know is I have a positive change. That means the force is acting in the direction of the object's initial motion. But look at this one here. Okay, so now look at this one here. If I take the area here, I'm going to say negative 150 times 4. So that's negative 600 joules worth of work. All that means is this work was done opposite the direction of the object's motion. So I end up getting negative 200. We can't have negative energy. That just means it ended up uh, uh, having 200 joules of kinetic energy when we're all said and done. Now, another thing you need to look at is graphs where we have a compressed spring that's pushing away. They like to ask this question, and the reason is because with spring force, remember, the spring energy rather is proportional to displacement square of the spring. So what that means is uh, if this was the spring is not compressed at all, I have no spring potential energy. As I push it this way, I'm going to increase the potential energy in the spring as a function of the square of the displacement. So when I've got it displaced to 0.2, I have 2 joules of energy. But if I double that, then I'm going to increase it by a factor of 4. It goes up to 8. Okay. Now I start off with a compressed spring, and I stuck a ball against a spring in a ball launcher. I let it go. What's going to happen is this is going to drop down as a square function to 0. And the kinetic energy is going to come up and take its place because the mechanical energy isn't going to change unless I'm told there's being work done, which usually I won't be told that. So the idea is if I know what the spring did, and I can tell because it's going to drop, when it gets halfway there, it's going to have a fourth the energy. That I just have to say, well, I know the mechanical energy stayed constant, so this minus this tells me what the kinetic energy is. Just remember that the two of them always have to add up to the mechanical energy I started with. Now we sometimes see these ones that look like this. So we have periodic motion. So if I see it, it makes a sinusoidal pattern. That means I'm talking about simple harmonic motion. So if I have simple harmonic motion, the first thing I want to think of is I can look at this and I can tell what the period is. The period is the amount of time it takes to complete an oscillation. So just go from peak to peak. Once I know that, if I know what the period is, I can use the period equation for a spring to find the spring constant or the mass. I can use the of a pendulum to find either g or the length of the spring. The amplitude on one of these graphs is going to tell me the maximum mechanical energy, or the mechanical energy, the maximum potential energy is going to be represented here. So 0.3 meters, if it's a spring, I can use the spring energy equation to say, well, now I know how much energy is present in this system. And no matter what, at all points in time, that energy will be the same. So at maximum displacement, all of the energy is in the form of potential energy. And at equilibrium, it's all in the form of kinetic energy. So if I have an oscillating system, when it's in position A, it's maximum displacement. So the object has no kinetic energy. It just has all potential energy. As it moves through the equilibrium point, notice it's moving in the negative direction now. At B, it doesn't have any potential energy. There's no spring force. There's no spring displacement. So it's all kinetic. So whatever the energy was here, it's all kinetic here. So I can find the velocity. And when it gets to here, it's compressed it again. I didn't do a very good job of that, but it compressed it, and now it's all potential energy. Again, it just keeps on going back and forth. Just remember, it's always potential at the peaks and the valleys, at the maximum displacement, and at equilibrium, it's always kinetic. So again, at the peak, I have maximum spring force. I have maximum spring energy. I have maximum spring force. I have maximum acceleration since I have maximum force. But what don't I have? I don't have any motion at this point. It has stopped at maximum displacement. Therefore, I don't have any kinetic energy. I don't have any velocity here. As I pass through equilibrium, I lose these completely. I have no spring force, so there's no acceleration, no force, no spring potential energy. What I have is maximum velocity and therefore maximum kinetic energy. And last thing, and I'll be done with this one right before the bell rings and you guys start coming in here. If I make a graph of potential energy or kinetic energy versus time, I'm going to have a period that's half as much. And this is a spring potential one here. So in this case here, there's no displacement, so there's no energy. Maximum displacement, so I have maximum energy. But here, I have maximum displacement in the other direction. That's still positive energy. So I have to come back to here at that point, right? And and at this point here, at 1 second, I'm passing the equilibrium. There's no spring force. There's no spring potential energy. So the energy goes to 0 at time 1. All right. So just remember that with these ones here, uh, here, 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 here. Those are all maxima of potential energy. And then here, 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 and here is minimus. Hey, thanks for watching. You guys are in good position for the AP test. Let's get practiced up and ready for it. Thanks for watching.